So hello everyone around the globe, in whatever time zone you have found yourself. I welcome you to the breakout session. The breakout session for today have a specific structure. There are 4 topics running in parallel. You are free to change between topics. And our topic is readiness for data for artificial intelligence and machine learning. The topic's structured this way, so you have 2 nearly identical sessions, and the non-identical bit is the discussion. So both sessions include several talks, and the talks are exactly the same. So there's no point for you to attend the talk twice unless you liked it very much. But the discussion sessions are distinct. So if you feel you didn't have all the questions answered during the discussion session, you're welcome to contribute to the second discussion. You also can contribute to the discussion while the speakers are talking. You can put your questions in the chat and we will prioritize and moderate them and then ask them during the discussion session. So do not wait, get ahead with that. And with this, I would like to go introduce our speakers and the panelists. The first speaker, so Alistair Forbes from National Physical Laboratory, United Kingdom. He will make an introduction to the topic, and Alistair is a fellow in the data science department. His interests lie in mathematical and statistical modeling, numerical analysis, and scientific computing. More recently, Alistair has been heavily involved with knowledge representation and knowledge-based reasoning. Alistair is a visiting professor at the universities of Huddersfield, at School of the Computing and Engineering, and Strathclyde at the Department of Mathematics and Computer Science. After Alistair has given an introduction to the team, Marcus Baer will talk about reference data for trustworthy machine learning in metrology. And Marcus is the head of Department for Mathematical Modeling and Data Analysis at the German National Metrology Institute, the BTB. And Marcus is also visiting professor in theoretical physics at Technical University Berlin. Marcus holds a PhD in physical chemistry from Prinz Haber Institute and Freie Universität Berlin, and he habilitated in the area of theoretical physics in 2003 at Dresden. The research fields of Marcus are metrology and modeling of measurement processes, collective motion and pattern formation in active matter, as well as modeling of non-equilibrium dynamics in biological systems. Marcus was the chair of MathMed, European Center for Mathematics and Statistics for Metrology between 2016 and 2019. And now Marcus is chairing the European Metrology Network for Mathematics and Statistics in EuroMed. During the panel discussion, we will be joined by Ian Gilmer. So Professor Ian Gilmer is Head of Science at the National Physical Laboratory, United Kingdom. Ian is a Senior Fellow and Visiting Professor at the School of Pharmacy at the University of Nottingham. He's a founding director of UK National Centre of Excellence in Mass Spectrometry Imaging, and his research goal is to achieve super-resolution label-free metabolic imaging. As a part of his work, Ian leads international standardization in surface chemical analysis and is chair of ISO Committee on Mass Spectrometry, as well as chair of VAMA's Technical Working Area 2 on surface chemical analysis. Ian is championing the topic of reproducibility in research, and as a part of his work, he hosted a workshop improving reproducibility in research, role of measurement science, in May 2018 at the National Physical Laboratory, UK. So with this, I would like to hand over to our speakers.
Hello, I am Alistair Forbes, a mathematician working in the data science department at the National Physical Laboratory, the UK's National Metrology Institute. I want to say a few words about this discussion session in the context of the SI Digital Framework Initiative. The SI provides a basis for the international measurement system. The aim of the SI Digital Framework is that all aspects of this measurement system, measurement results, uncertainties, traceability, calibration, and so on, can be accessed and interpreted digitally, enabling machine-to-machine communication, enabling the analysis of data by computer systems, for example, statistical analysis, finite element analysis, computational physics and computational chemistry calculations, and also the analysis by artificial intelligence and machine learning systems. The framework envisages 3 layers: the core layer, a service layer, and an applications layer. The SI core layer is concerned with the basic elements of measurement, representing measurement results in terms of a numerical value, associated unit, and uncertainty. The service layer is concerned with the wider services and products provided by the national metrology institutes and similar organizations that directly support the integrity and traceability of the measurement system. The applications layer is concerned with tools and services developed and deployed in the broader scientific and technical community, and includes analysis and artificial intelligence and machine learning methods. This discussion session primarily relates to the applications layer. The FAIR principles feature strongly in this workshop. These principles are aimed at improving the findability, accessibility, and reuse of data, particularly by computer systems operating with little or no human intervention. The FAIR principles are there to help machines perform tasks that are useful for us. While the immediate aim of the SI digital framework is to provide machine-readable data, this longer-term aim is to provide machine-actionable data. The data should enable interpretation, analysis, reasoning, and decision-making by computer systems, again, operating without human intervention. And for this to happen, the computer systems must, in some sense, understand the meaning of the data. So the correct interpretation of data will generally require an appropriate knowledge, representation, and reasoning framework, employing controlled vocabularies, taxonomies, ontologies, and the like, and inference tools based on logic and statistical inference, for example. There are many issues that you may want to discuss in this session. One topic of interest is how can we ingest data and metadata into analysis systems. So we want to make sure that technical data is represented correctly. But we must also be concerned with the FAIR principles. In particular, the data must specify what individual or system it relates to, what physical artifact, what individual, which chemical compound material, and so on. And this is really what findability in FAIR is about. A second topic is how we assure and assess the trustworthiness of the outputs of analysis systems. A fundamental aim of metrology is to ensure that measurement data used in analysis is trustworthy, but we're also concerned with the trustworthiness of the outputs, not just the input data. And this presents a particular challenge when the outputs depend on training data, depends on models, depends on algorithms and software. So a related topic is how can we encode the provenance of models and algorithms and software in workflows. We may be able to specify the provenance of the data, but how do we specify or encode the provenance of the model, algorithm, and software underlying the analysis? I hope you enjoy the discussion session. I now pass you back to the chair of the session.
I will talk about the potential role of reference data for trustworthy machine learning and artificial intelligence algorithms, taking a methodological viewpoint. In the first part of the talk, the relation between machine learning and metrology is discussed, and in the second part, I will present a use case stemming from a European project in a medical physics application, and finally, I hope that this will give some ideas what could be potential paths towards standardization. For the role of machine learning and metrology, I can cite results from an artificial intelligence survey conducted among 14 European NMIs in the framework of the European network MASMET, which is a part of Euramet. And here this relation was considered from two different angles. So one viewpoint was, are there things metrology can contribute to artificial intelligence? Can it improve these methods? And the other direction was, in what sense do these new algorithms are extending the capabilities of metrology? And on the first item, obviously classical quality infrastructure aspects such as uncertainty, traceability were mentioned. Robustness, explainability are other things which you would like to have for a solid metrological assessment of artificial intelligence results. On the other hand, of course, there's many computationally intensive metrology applications where artificial intelligence algorithms may be beneficial or enabling. I listed some typical tasks which are often difficult to solve, and in particular here new applications of distributed measurement systems such as sensor networks or in general systems which produce a lot of data are potential beneficiaries. Okay, so from the results of the survey, there were less answers for the potential of AI for metrology, but certainly handling of big data is in the bigger NMIs an issue. Again, sensor networks, distributed systems feature highly, and it was also sometimes said that systems metrology is an emerging field. So there will be more and more systems where large number of measurements are combined. Another area, of course, highly resolved imaging and microscopic processes where a lot of pixels are produced. More answers came in the direction of how metrology can support for artificial intelligence. A potential connection was in particular seen in transferring ideas on uncertainty and traceability. And there, obviously, one main issue is how the input of measurement uncertainties affects the outcome of artificial algorithms and what procedures enable this determination. And the second most cited application there was reference databases, and that's actually the topic of my talk. And that could be measurements, but I will also have an example in a minute on simulation data. The general issue is, of course, data quality is a possible basic way to assess the suitability of a reference database. And all of this feeds into standardization, obviously. For future research priorities, consequently, trustworthiness, security, and contributing to quality infrastructure was mostly cited. Training data quality featured high in the column on the reliability, which in general seemed to be the most important concern for metrology institutes. I will not say much on explainability today, but certainly traceability with the uncertainty issue is a main concern, and examples in metrology should be identified and are important to put this area forward. So I will give you an example which comes from a project in the European Metrology research program, MPIR, and that is metrology for electrocardiographic automated data analysis. It's running a project called Metadata. We reached halftime now, and the two main objectives is, first of all, to assess metrology for advanced data analysis, including machine learning. And the second part is to provide reference data for these artificial intelligence, actually to enable such benchmarks. And here we started from a clinical ECG database, which is called PDB-XL. And the goal of the project is nevertheless to extend that and to provide a data base made out of synthetic data with a ground truth. And that means they will be generated by established biophysical models. And there you know exactly what you put into the simulation, what kind of pathology is implemented in the model, and how it affects the ECGs. And obviously, hopefully, if this all is successful, it will further clinical applications and standardization in this important practical point. So a reference database of measured clinical reference data is PTB-XL. It has 20,000 ECG recordings of 10 seconds duration, and in each of these records are 12 leads measured. And for each of the recordings, we have a diagnostic and rhythm statement from two experienced cardiologists who use the well-known ISO standard classification, and that leads to separation of the whole database in superclasses. So about half of the ECGs were from healthy, normal people. Then there's different pathologies, and each of these pathologies goes again into subclasses. This was done in collaboration with the Fraunhofer Heinrich Hertz Institute and is published in Scientific Data. Now, with this database being available, there was a first benchmark carried out for different types of machine learning algorithms and also some conventional signal processing algorithms such as wavelets. You can see the results. In general, it was found that machine learning is superior with high success rate at above 90% compared to all conventional previously used algorithms, especially ones who extract features, which is often what software in the practical doctor's practice will do. And then also first steps were done towards explainability. As I said, this is not the main feature, but you can use this information also to identify the parts of a 12-lead ECG record which have most influence the classification in one particular illness class. Again, this is also just published by our Fraunhofer colleagues in collaboration with PTB. But the main point of the project was its new aspect, implementing a modeling pipeline. And here that requires modeling of the ventricles and the atria of the heart. Here the ventricle part is shown. So you define mathematical equations and you run them. And first it's done on the isolated surface of the heart where you can make catheter measurements and validate these models, so that all has been worked out already. And then in a second step, to get the ECGs, you have to embed them into torsos. And here we have a cohort of 13 models taken from direct medical imaging recordings, different hearts embedded in different torsos, obviously, and the black dots in each of the pictures are the points where the ECGs are taken. Okay, and if all of this is put together, you can simulate ECGs for each of these people. You can also put pathologies in the cardiac dynamics, which are often mechanistically known, and then you get the resulting ECG here plotted in a typical version that doctors are familiar with. And you can also superpose noise. So in other words, you can vary the quality of the data and then see how that may affect the machine learning algorithm. The main goal is actually to test such algorithms with well-defined data records. Okay, and that brings me already to the summary. In short, I discussed a bit the issues that metrologists found important in trustworthy machine learning. Main conclusion is, of course, training data are key. And in particular, we have a lack of quite high quality references. So we should work to set up reference databases and also find criteria to assess these databases. And that would be measurement data. But another second path, which is very promising, is to use synthetic reference from digital twins. The medical example I showed is already very complex with respect to the processes and equation setup, but obviously this can be beneficial probably in simpler, better understood physical processes. And hopefully if these things can be established, they can be an important element in the standardization rules for such processes. Thank you very much.
So hello, I can hear myself. Is that a problem?
We can hear you.
Yeah, we think we can.
Yeah, I just mute so the dog doesn't bark. All right. So for the purpose of the panel discussion, do we want to start then with the question from Mauricio? This idea of how does one validate the quality of a digital twin?
I guess this one comes towards me. Yeah, the one thing is, of course, you can have more. I mean, you have to have actual recordings. You have to have a representation of reality by measurements. In the case of ECG, you have, of course, ECG recordings, and usually it's first validated by ECGs combined with medical imaging and possibly measurements on the hard surface and so on. So you need really to check if your model is reflecting reality. Now, in the case of this medical assessment, you need also to have the variability, and that's why we also needed this clinical database to start with. Because in the end, diagnosis will not be made on always on the same object, but it will be made on a population. So you have to have the variation in the population. This is a specific case, and that may differ in other applications, but in general, always having test measurements, in some cases having phantoms to simplify the measurement process, or to put in what you want, or to know what you put in is very important. So you need always a validation and a relation between the real data set and the virtual ones. And if you're confident about that, you can go on and possibly extend parameter space and then produce more virtual data then.
Great, thank you for that answer. Fernando asked a fantastic question that I was thinking about as well. This idea, and this gets a little bit towards ground truth and what is ground truth. How do the uncertainties associated to training data, how can they be combined with the statistical uncertainty of the machine learning algorithm? This idea that we have a quantity that's measured that has an error bar on it, and how does that propagate through as we model it?
I guess that's a very good question. That's a topic of current research, of course, more in the machine learning communities than in metrology, where machine learning applications just start. But obviously, concept like Monte Carlo would go into that. So if we know the uncertainty, if it's well characterized, we can vary also the training data a bit. So that's a common route, which is analogous to things we do in metrology. But it's really something which isn't completely as well characterized as standard uncertainty calculations, I should say. Yeah.
I think another question that the metrology community is always interested in is, what is the sensitivity of the outputs of the analysis to changes in the input data? And one of the worrying aspects of machine learning algorithms is that a small change in the input data can completely change the classification that's produced by a machine learning algorithm. So I think, issues to do with the sensitivity of the outputs of machine learning algorithms to changes in the data that can be plausibly described in terms of uncertainty in the measurement data. If you did experiment again, you get different measurement data. How much would the machine learning output change because of this new experiment?
Thank you. The next question will be coming from Thomas Engel at Marcos. And the question is, for AI training and application, the consistency of input data quality matters. Even improved input data may confuse an AI. What is your opinion about this?
Yeah, that's a good point, and that's something we also only start tackling. I mean, obviously, it would be good to have criteria of statistical evaluation of these input data. For example, if you would produce data which have a bias, I mean, if you have a lot of data which are all consistently, hopefully, and you add data possibly recorded from another setup, another realization of the machine which has a bias, you already a bit in trouble. But that's something which I would see as an important aspect of data quality. I mean, there's certainly the aspects that the data should be in the right format, the principles Alistair has alluded to, but certainly having some statistical evaluation processes need to be developed here also. Yeah, I mean, that's true. More data do not always improve things. I mean, it should always, in principle, that's what the machine learner tells us. That they should, but it has to be clear that this data are consistent. And
that's an interesting point. So there is additional question coming from Alex Walke, and he's asking whether it is thinkable to elaborate a digital twin of a laboratory and then perform calibrations without much control of the environmental parameters, but measuring the parameters in real time and maintain the measurement uncertainty.
That's a good question, and in some sense, one of the aims of metrology is to provide traceability of measurement in industry, in the shop floor. How do we do that? We know how to provide traceability in the laboratory because we control the environmental effects. But if we've got digital twins of how these effects, environmental effects, affect the measurement result, and often we do, then it seems potentially possible that through this digital twin, we can add valid sense of data describing the environment. We can correct the measurement results at the time of measurement relating to the environment that the measurements are actually placed in. So I think that is more or less doable. And we've already undertaken projects where that is the aim.
Thank you. So the next question is, in terms of fair data, how can we model annotated data? Do we have considered the ground truth labels in data in fair format? I'm not sure I understand the question completely. So could you clarify, please? I think it's Mohammed Mozafari. So feel free to post another question in chat. In the meantime, I have a question of my own. I think it's interesting. So the part of the question, what has been highlighted that having more data is not necessarily better if it's not the right data, even if it's good quality data, and also if we don't have the process which knows how to deal with it. With these additional data sets. For me, one of the issues is access to the data. So if we want to have a digital twin, how do we create such twin? And is there anything as an NMI we should be thinking about which reference data sets we prioritize, which we'll need to create, which we'll need to be holding? So what do you think about this, Bob, so everybody on the panel? So what is our role as a national measurement institutes in with respect to reference data sets? Because at the moment, only some of us have some of this reference data set. It's not even agreed that we're doing it.
I think that's a good question, Marina. And as the discussions were going on, I was thinking very much on this thing is, we run many different kinds of intercomparison studies. There's CCQM pilot studies, there are things like BAMAS into laboratory studies, and they all create data, but we don't usually kind of harvest that data and curate it into something that could be considered a tested reference data. In my own area, actually, in TWA2, we've recently just had a project doing something a bit like this, where they've used a synthetic data set for machine learning and then evaluated that on different kind of experimental configurations. And that's a data set, in a sense, has got some level of provenance to it, but then how do we as a community of NMIs kind of provide an index or a catalog of these kinds of reference data sets?
An earlier discussion touched on this, and to the extent that do we need a quality infrastructure, or how should we expand the quality infrastructure to take into account trustworthiness of computation, which is really what a digital twin is. And the digital twin will embody models, it will embody reference data. And how do we qualify a digital twin in terms of, is this digital twin in some sense traceable to some gold standard? And I think these are issues that the metrology community and others, are trying to address one way or another. So I think it's a very important aspect.
And I think also to the point that was raised earlier about this kind of machine actionable, and if it's machine actionable, is how confident is the machine going to be in that data set? So it kind of then leads on to the thinking of, well, there needs to be some kind of quality, as Alistair was saying, some kind of quality index behind that data. Perhaps that's scored based on reuse of the data that could be measured, or comments on the data, or the number of pilot studies or key comparisons that are connected to that data. That gives kind of provenance and some rigor to that data. But a machine does need to have some parameter, I would imagine, that thinks, yes, that's kind of like a gold star data set, or it's perhaps not so good a quality as that.
Yes, it's very interesting. I believe there is a potential to learn from other several metrology networks, including Earth observations, where they are coming out with a data usefulness or data quality matrix, which has sort of multiple parameters in several dimensions.
Also, Marina, your question also reminded me about one of the earlier discussions we had already today, and that was a bit on the aspect of research data management, which is actually not happening only in metrology, but it's happening in all the sciences. So at least in Germany, we have now a big national initiative. So as also Ian and Alistair said before, it becomes more and more obvious that often data are not really completely used, just the end result, and there's a lot of important information on the way that you always discard. So research data management is precisely about that, and it should have, of course, these aspects as having additional information on how the data was produced, which software was maybe used to process it from one stage to another, and all these aspects. And metrology maybe has these data management initiatives that we have, say, in Germany, have always this one side, which is the applications, what is the need of the users, but then there always needs to be some kind of a core description, and that's where quality infrastructure and the more generic and unifying way of metrology can play a big role. I mean, we will not do that alone, but there we can contribute and hopefully learn back about more complex applications, which we would see as emerging fields in metrology then. Yeah.
Mm-hmm. There is a next relevant question coming from Martin Koval from the Czech Metrology Institute. And he would like to find out how do you see the reusing of old data for the purposes of AI? So a lot of NMIs have, sorry, my question just disappeared. A lot of NMIs have a lot of measurement data, which is used only once, but it's stored for disjoint cases, such as wrong calibration, etc. I think it touches quite closely to us, so to what Ian said about collecting data and not reusing it, and how can we do it better, and basically assigning the value to data. So are you familiar with any initiatives which we could learn from to benefit from the experience on the data reuse and successful data quality indexing?
I think that's a very good question, and it sort of goes back to an earlier question about can we use environmental data in order to provide up-to-date uncertainty contributions. So I firmly believe that we're doing recalibrations of the same artifact many times, and we're taking measurements of the environment, but all that data is just isolated. We've got no opportunity to learn because that data isn't fair. It's not accessible, and we can't machine action it because it's hidden away somewhere. And I think there are opportunities, massive opportunities for NMIs to learn about the performance of their instruments and the performance of artifacts by having that time series and being able to analyze that data using statistical analysis or machine learning and the like. So I've got a question for Marcus, for instance, the 20,000 ECGs, that's a tremendous resource. What effort has been made to make that data sets fair, and have we a measure of a benefit that having that data set has been in terms of improving research in ECGs and heart medicine, for instance?
Good question. I don't know actually all the details there because these data sets have been collected a while ago and they have somehow lying somewhere. So maybe that's a good example of historical reuse. And basically what these publications I referred to was make them usable for the public, because some years ago it was still said, well, this was done with taxpayers' money, so we should always put a fee on it. And then so, which actually was a big obstacle for the outside community to using them. So when we started developing more these ideas of open data and so on, we said we should let's try to rework that, and we did do that together with the Fraunhofer colleagues and the machine learning experts, and they have done all kinds of checks. So they really so that was precisely what this publication scientific data was about, to check them, to see if there's inconsistencies and so on, and clean up the data a little bit. I think the one good thing was that the PTP a while ago has really always said there's these two cardiologists, and they have said a bit more than just standard ISO diagnosis. They also put a bit like how sure they are and so on. So there was quite a bit of information which had already a bit of a metrological angle, but really the data had to be really reworked, formatted, put in. It's now in Physionet, which is a worldwide database, and so this certainly was an effort to apply and make them consistent with the FAIR principles.
I think one of the things that surprises me is still there seems to be very little measurement of the reuse of data. So, for example, in publications, we look at Google Scholar all the time and we can see our citation metrics. That drives good and bad behavior, let's say. But in the world of data, you kind of would expect there'd be a very established good infrastructure now to see how many times data is reused, where it's been reused, which AI things maybe it's been fed into, what the outputs of that. Kind of, I would expect that all to be available, and it isn't, and it continues to surprise me. And I think if it was available, it would drive a lot of good behaviors. I'd be interested to know what any comments are on that, because it seems to me a big gap that's still not filled.
Jason, can I bring you in here? I know that the national laboratories in the US have operate under a principle that public-funded research should lead to publicly available results. Is there a requirement for national labs in the US to provide open data?
We haven't gotten quite to the point of it being an absolute requirement. Generally speaking, particularly at NIST, we are increasingly publishing our data via GitHub or data.gov, particularly data that's relevant to manuscripts and publications.
Yeah.
I have to talk to the folks at like PML who do the sort of physical standards and ask them if this is sort of permeated out into their more mistraceable activities.
Yeah, I think we're at NPO, we're doing very similar now. So kind of mandating people to make the data, or will be soon, publicly available where it's publicly funded. And that we in the UK, this is open. There's Concordat on open data, which we would hope to be signing up to soon.
But also coming back to your remark, Ian, this is also, I think, is really just starting the harmonization we have, of course, in metrology in the more conventional sense we have in fields, but in all areas, in many areas of science, there isn't really this established standards. And looking in this, just the national example of Germany's research data initiative, that what you can see is the disciplines which are leading there are the ones where the need naturally arose. So it's astrophysics, particle physics, which I mean, which create zillions of data, which apply all kinds of sophisticated software, and so their consortia seem to be naturally flowing from what they do anyway, and probably, but then many other of the smaller areas do not have such a consistent network, and it's quite surprising that I mean, everyone says immediately, "Oh, yeah, that should be a good thing," and we know, in a sense, we waste quite a lot of effort, and we reduplicate often things just because we don't have, especially small laboratories often don't have the means. So it's really something, yeah, that's starting, and metrology in a way is also in an early phase of that. I mean, you could see that big data handling, even though new algorithm, there is an interest in some institutes, but most of them see more, there should be this harmonization analogous to what we do in metrology, but really, so basically in Germany, the way to move forward was, the initial idea was to do it bottom up. The ministry says, so who will get national funding or maybe European funding should follow these and these principles in order to make use of these valuable data, which usually are just buried in the supplements of publications or not visible at all or not accessible at all. So, but then they said, no, but maybe the better way is to go the other way around. We look at the different communities and let them all develop first in the communities and a harmonic approach, or an approach they think is fit for their purposes, and then maybe all of this in the end over some 5 to 10 years or longer will grow up in some national infrastructure. And but that's really a process that seems to be starting. I don't know, it would be interesting to hear how it is in UK, US, or in other countries.
And there is a next question coming from Fernando Kornblit. And it is, what do you think about blind calibration for sensor networks? That is, if you calibrate only a few sensors and then transfer the traceability to the others based on mathematical models.
And that also depends a lot on the metrology behind the sensors themselves, whether they, from a physical point of view, whether they're reproducible and repeatable.
Yeah. We've been working on that problem in relation to air quality, where we've got traceable reference sensors, but many more low quality sensors. And so we're trying to calibrate a network of low quality sensors against a reference network. And, you know, the mathematics of it is just about there. The uncertainty quantification is just about there. But you are heavily dependent on the models being correct, and you're heavily dependent on the independence of the reference network, when in fact the reference network probably has a significant amount of correlation. So the information you think you've got isn't nearly as rich as it actually is. But I think it's certainly a doable, and it's worth trying.
Okay. Okay, so we are about to close the session. There will be a 10-minute break. and everybody will be coming back at 13:55. If you feel you have more questions, please post them in chat, and if there is time, we'll address them in a second discussion session. So thank you very much. Okay. So, hello everyone. Welcome to the second round of the breakout sessions. We are in the readiness of data for artificial intelligence and machine learning. And today we have two talks. And the first talk is given by Alistair Forbes. So Professor Alistair Forbes is a fellow in data science department at the National Physical Laboratory, UK. And he has interests in mathematical and statistical modeling, numerical analysis, and scientific computing. More recently, Alistair has been involved and working on knowledge representation, knowledge-based reasoning. Alistair is a visiting professor at the University of Huddersfield at the Department of Computing and Engineering, and University of Strathclyde at the Department of Mathematics at the Department of Computer Science. The second talk will be given by Markus Baer from German Natural Metrology Institute, the PTB. Markus will be talking about the reference data for trustworthy artificial intelligence and machine learning in metrology. and Marcos is leading the Department of Mathematical Modeling and Data Analysis at the PTB. And he's also a visiting professor in theoretical physics at the Technical University Berlin. Marcos holds a PhD in physical chemistry from Fritz Haber Institute and Freie Universität Berlin, and he habilitated in the area of theoretical physics from Technical University Dresden. His research fields are metrology and modeling of measurement processes, collective motion and pattern formation in active matter, as well as modeling of non-equilibrium dynamics in biological systems. Marcos was chair of MathMed, so the European Center for Mathematics and Statistics in Metrology between 2016 and 2019. And currently Marcos is chairing the European Metrology Network for Mathematics and Statistics in Euromed. During the panel discussion, Marcos and Alistair will be joined by Professor Ian Gilmer, who is the head of science at the National Physical Laboratory, United Kingdom. Ian is a visiting professor at the School of Pharmacy at the University of Nottingham, and he's a founding director of the UK's National Centre of Excellence for Mass Spectrometry Imaging. So Ian leads several standardization initiatives in surface chemical analysis, and he's chairing ISO 201 in mass spectrometry, as well as chairing VAMA's technical working area 2 on surface chemical analysis. Ian is championing the topic of reproducibility in research, and as a part of it, he hosted a workshop on improving reproducibility in research, the role of measurement science at NPL in 2018. During the session, my co-chair will be Jason Hattrick-Simpers from NIST, National Institute for Standards and Technology, so American NMI. Jason is waving. I think Jason is heavily working in artificial intelligence application in material science. So with this, I would like to hand over to our speakers.
Hello, I am Alistair Forbes, a mathematician working in the data science department at the National Physical Laboratory, the UK's National Metrology Institute. I want to say a few words about this discussion session in the context of the SI Digital Framework Initiative. The SI provides a basis for the international measurement system. The aim of the SI Digital Framework is that all aspects of this measurement system, measurement results, uncertainties, traceability, calibration, and so on, can be accessed and interpreted digitally, enabling machine-to-machine communication, enabling the analysis of data by computer systems, for example, statistical analysis, finite element analysis, computational physics and computational chemistry calculations, and also the analysis by artificial intelligence and machine learning systems. The framework envisages 3 layers: the core layer, a service layer, and an applications layer. The SI core layer is concerned with the basic elements of measurement, representing measurement results in terms of a numerical value, associated unit, and uncertainty. The service layer is concerned with the wider services and products provided by the National Metrology Institutes and similar organizations that directly support the integrity and traceability of the measurement system. The applications layer is concerned with tools and services developed and deployed in the broader scientific and technical community, and includes analysis and artificial intelligence and machine learning methods. This discussion session primarily relates to the applications layer. The FAIR principles feature strongly in this workshop. These principles are aimed at improving the findability, accessibility, and reuse of data, particularly by computer systems operating with little or no human intervention. The FAIR principles are there to help machines perform tasks that are useful for us. While the immediate aim of the SI digital framework is to provide machine-readable data, this longer-term aim is to provide machine-actionable data. The data should enable interpretation, analysis, reasoning, and decision-making by computer systems, again, operating without human intervention. And for this to happen, the computer systems must, in some sense, understand the meaning of the data. So the correct interpretation of data will generally require an appropriate knowledge, representation, and reasoning framework, employing controlled vocabularies, taxonomies, ontologies, and the like, and inference tools based on logic and statistical inference, for example. There are many issues that you may want to discuss in this session. One topic of interest is how can we ingest data and metadata into analysis systems? So we want to make sure that technical data is represented correctly. But we must also be concerned with the FAIR principles. In particular, the data must specify what individual or system it relates to, what physical artifact, what individual, which chemical compound, material, and so on. And this is really what findability in FAIR is about. A second topic is how we assure and assess the trustworthiness of the outputs of analysis systems. A fundamental aim of metrology is to ensure that measurement data used in analysis is trustworthy. But we're also concerned with the trustworthiness of the outputs, not just the input data. And this presents a particular challenge when the outputs depend on training data, depends on models, depends on algorithms and software. So a related topic is how can we encode the provenance of models and algorithms and software in workflows? We may be able to specify the provenance of the data, but how do we specify or encode the provenance of the model, algorithm, and software underlying the analysis? I hope you enjoy the discussion session. I now pass you back to the chair of the session.
I will talk about the potential role of reference data for trustworthy machine learning and artificial intelligence algorithms, taking a methodological viewpoint. In the first part of the talk, the relation between machine learning and metrology is discussed, and in the second part, I will present a use case stemming from a European project in a medical physics application. And finally, I hope that this will give some ideas what could be potential passes towards standardization. For the role of machine learning and metrology, I can cite results from an artificial intelligence survey conducted among 14 European NMIs in the framework of the European network MASMET, which is a part of Euramet. And here this relation was considered from two different angles. So one viewpoint was, are there things metrology can contribute to artificial intelligence? Can it improve these methods? And the other direction was, in what sense do these new algorithms are extending the capabilities of metrology? And on the first item, obviously classical quality infrastructure aspects such as uncertainty, traceability were mentioned. Robustness, explainability are other things which you would like to have for a solid metrological assessment of artificial intelligence results. On the other hand, of course, there's many computationally intensive metrology applications where artificial intelligence algorithms may be beneficial or enabling. I listed some typical tasks which are often difficult to solve, and in particular here new applications of distributed measurement systems such as sensor networks or in general systems which produce a lot of data are potential beneficiaries. Okay, so from the results of the survey, there were less answers for the potential of AI for metrology, but certainly handling of big data is in the bigger NMIs an issue. again, sensor networks, distributed systems feature highly, and it was also sometimes said that systems metrology is an emerging field. So there will be more and more systems where large number of measurements are combined. Another area, of course, highly resolved imaging and microscopic processes where a lot of pixels are produced. More answers came in the direction of how metrology can support for artificial intelligence. A potential connection was in particular seen in transferring ideas on uncertainty and traceability. And there, obviously, one main issue is how the input of measurement uncertainties affects the outcome of artificial algorithms and what procedures enable this determination. And the second most cited application there was reference databases, and that's actually the topic of my talk. And that could be measurements, but I will also have an example in a minute on simulation data. The general issue is, of course, data quality is a possible basic way to assess the suitability of a reference database. And all of this feeds into standardization, obviously. For future research priorities, consequently, trustworthiness, security, and contributing to quality infrastructure was mostly cited. The training data quality featured high in the column on the reliability, which in general seemed to be the most important concern for metrology institutes. I will not say much on explainability today, but certainly traceability with the uncertainty issue is a main concern, and examples in metrology should be identified and are important to put this area forward. So I will give you an example which comes from a project in the European Metrology research program, EMPIA, and that is metrology for electrocardiographic automated data analysis. It's running a project called Medalcare. We reached halftime now, and the two main objectives is, first of all, to assess metrology for advanced data analysis, including machine learning. And the second part is to provide reference data for these artificial intelligence, actually to enable such benchmarks. And here we started from a clinical ECG database, which is called PDB-XL. And the goal of the project is nevertheless to extend that and to provide a data base made out of synthetic data with a ground truth. And that means they will be generated by established biophysical models. And there you know exactly what you put into the simulation, what kind of pathology is implemented in the model, and how it affects the ECGs. And obviously, hopefully, if this all is successful, it will further clinical applications and standardization in this important practical point. So a reference database of measured clinical reference data is PDB-XL. It has 20,000 ECG recordings of 10 seconds duration, and in each of these records are 12 leads measured. And for each of the recordings, we have a diagnostic and rhythm statement from two experienced cardiologists who use the well-known ISO standard classification, and that leads to separation of the whole database in superclasses. So about half of the ECGs were from healthy, normal people. Then there's different pathologies, and each of these pathologies goes again into subclasses. This was done in collaboration with the Fraunhofer Heinrich Hertz Institute and is published in Scientific Data. Now, with this database being available, there was a first benchmark carried out for different types of machine learning algorithms and also some conventional signal processing algorithms such as wavelets. You can see the results. In general, it was found that machine learning is superior with high success rate at above 90% compared to all conventional previously used algorithms, especially ones who extract features, which is often what software in the practical doctor's practice will do. And then also first steps were done towards explainability. As I said, this is not the main feature, but you can use this information also to identify the parts of a 12-lead ECG record which have most influenced the classification in one particular illness class. Again, this is also just published by our Fraunhofer colleagues in collaboration with PTB. But the main point of the project was its new aspect, implementing a modeling pipeline. And here that requires modeling of the ventricles and the atria of the heart. Here the ventricle part is shown. So you define mathematical equations and you run them. And first it's done on the isolated surface of the heart where you can make catheter measurements and validate these models, so that all has been worked out already. And then in a second step, to get the ECGs, you have to embed them into torsos. And here we have a cohort of 13 models taken from direct medical imaging recordings, different hearts embedded in different torsos, obviously, and the black dots in each of the pictures are the points where the ECGs are taken. Okay, and if all of this is put together, you can simulate ECGs for each of these people. You can also put pathologies in the cardiac dynamics, which are often mechanistically known, and then you get the resulting ECG here plotted in a typical version that doctors are familiar with. And you can also superpose noise. So in other words, you can vary the quality of the data and then see how that may affect the machine learning algorithm. The main goal is actually to test such algorithms with well-defined data records. Okay, and that brings me already to the summary. In short, I discussed a bit the issues that metrologists found important in trustworthy machine learning. Main conclusion is, of course, training data are key. And in particular, we have a lack of quite high quality references, so we should work to set up reference databases and also find criteria to assess these databases. And that would be measurement data, but another second path, which is very promising, is to use synthetic reference from digital twins. The medical example I showed is already very complex with respect to the processes and equations set up, but obviously this can be beneficial probably in simpler, better understood physical processes. And hopefully if these things can be established, they can be an important element in the standardization rules for such processes. Thank you very much.
Okay.
Where is it? Oops.
Fantastic. So now we're going to start the discussion portion of the breakout session. First of all, would like to encourage you all to continue adding questions to the chat. We'll pull them up and pull them in as is necessary. One of the places that I'd like to start with is this question from Emilio. I really like it. What I consider most crucial, regardless of the format used to express the measurement results and their uncertainty, is the ability that measuring the machines may have to decide on their metrological state in relation to their tolerances and maximum permissible errors. In view of the uncertainty reported in the DCC, how do you see this issue?
Well, thank you, Emilio. So one of the goals of metrology is to provide traceability of measurement at the point of measurement in the industry floor and the laboratory and the like. And the quantum SI in some sense helps enable that, because we can have access to references on a sensor. But I think one of the new capabilities of the digital approach to this is that we can provide new sort of services, new capability. And one capability is for an instrument to self-assess what state it's in, as you say, Emilio, and say, and compare that with the requirement for the measurement. Okay, I'm being asked to do this task. This is uncertainty budget or the tolerance for this task. Am I capable of making that measurement on the basis of my current behavior, on the basis of the current environment? And so if the instrument had on board a sort of a digital twin of that instrument, it would be well capable of making that assessment and say, I'm in a state that's sufficiently good to make this sort of measurement to that sort of tolerance, or return the answer, say, no, come back in an hour when environmental conditions are better. So I think Amelia's question is opening our eyes to sort of new capability that a SI digital framework could bring.
Thank you, Alistair. I have actually the next question, and this is slightly woolly, but it is: how do you see the role of NMIs with regard to this AI and ML systems in intermediate, short-term, and long-term future? And the question relates not just to reference data sets, but also to the fact that there is, on one hand, a need on reliable and reproducible, trustworthy machine learning systems, yet this need is not necessarily realized in the process at the point of production of such systems. As NMIs, we are very well placed to actually bring physics and traceability and uncertainty tracing into the systems, yet this is not done. So some initiatives exist. So Marcus has held an excellent talk on this medal care, how medal care project has achieved it. How can we move forward to provide this sort of physical reasoning to this AI systems on the international, national levels?
Let's try. I mean, I read also the short version of your question just in front of me. I think really the role of metrology is probably more defining the rules and giving advice on how to generate and evaluate such data set. That's certainly true. So our role is probably very strongly in the quality infrastructure. But on the other hand, it's very beneficial if we can keep some examples, and we have to work with examples. It's a bit maybe compared to what has happened, I don't know, 30 years ago when the rules for measurement uncertainty were developed. Of course, there were some general rules which were firmly established with this GAM, but also ever since there have been discussions: can that be applied? Are there extensions needed? There's quite a lot of supplements. I think NPL has taken a leading role there, among others. And so basically, I think we need both things. I mean, in some of the areas where our competence is also in the measuring, Earth Observation Center and NPL has been mentioned. Medical data and PTB is quite strong, and other NMIs have other strengths. So then we should deal with this data, and because these data are very much sought for, and we have worked them out according to our rules, we get a natural link to the machine learning community. I think we said in the morning discussions already, this is of course not something we can achieve on our own. We have to really understand what the larger scientific community, the experts in machine learning, are doing, while they may look at us as people who can be trusted to provide well-characterized data, who know how to handle data and so on. So it's really, both aspects are important. I think metrology will not be the main hub for reference data. They will appear everywhere in science, and there is a larger process going on where data are now considered as much more valuable, and research data management infrastructures are placed all over science, but really still we need some of these examples to work out how to go forward here. Yeah. As a third short summary here.
Thank you.
Yeah, okay. So next question from Mohammed. We have a problem, right? Besides using AI in this sort of post-mortem manner where we're analyzing measurement data, we're increasingly pushing them into smart measurement devices. And so the question is, and well posed, should the calibration procedures be adapted to cope with the influences of AI components in these devices?
Yeah, great question, Mohammed. So I think you're absolutely correct. And part of this meeting is really about what the quality infrastructure needs to do to accommodate the fact that the measured result, the output of an instrument is no longer a needle indicating pressure or whatever. It's a digital readout or whatever that is a result of a lot of computation. Some of that computation might be finite element analysis, some of that computation might be statistical analysis, and some of that computation may be application of a machine learning and AI algorithm. And then the question arises, well, what is the uncertainty component due to that computation, due to that software, and how do we quantify that? And so I think and we're using lots of smart meters that are making these adjustments, calibrating themselves on the basis of the environment. We have smart meters that are maybe changing the analysis of data because they're changing the algorithms and software that's implemented because a new version of software has been downloaded. How does that affect traceability? And the quality infrastructure, the NMIs and the standards bodies and so on, and the accreditation bodies, are working hard to try and understand these issues and come up with solutions that are practical and also solutions that benefit our end user community.
Thank you, Alistair. So the next question is coming from Mauricio Alberini, and it is, if you make a digital twin of a process, will the uncertainty of the twin be greater than the uncertainty obtained by measurement?
I would say there's certainly additional things to consider. I mean, obviously, if we could do a perfect digital twin, we may be competitive, but usually the processes we want to model are very complex. So we use, in a way, simplified models. Often the issue is running them efficiently and fast. So we use, say, something like surrogate models, or even neural networks may be used in this context as well as being trained by simulation data, for example. So I would say that this is something always important to consider. I think we, in previous discussions, I guess, Alistair and others have said we have now this subject of uncertainty quantification, and that has much to do with telling what the model, how good are the models that we do, that we use, and how much do the approximations matter in terms of making the result more uncertain or adding to the uncertainty. So in many of these questions where models are interlinked with processing data, or for digital twins as well, you have to take also to account what is really the simplifications in the model errors, what is possibly the processes or approximation schemes we used, and what would they contribute to that. So there is additional components of uncertainties. Yeah,
I think a related issue, or perhaps it's the same issue, is when do we measure and when do we model and compute? So sometimes it's just a lot cheaper to measure, but the other circumstances it's impossible to measure. And Jason, in terms of materials modeling and things like that, there may be materials properties that is almost impossible to measure, but we might be able to compute them from ab initio molecular modeling principles and the like. And getting the right balance is sometimes not straightforward. I don't know if you have any comments on that, Jason.
Sorry, I was just in the process of writing up a question very central to that. So we have a issue that we have our models need to be able to identify, like our typical physical models, our ab initio models, our fluid dynamic models are brittle, right? They work in a regime of known capability, and then when you push outside of them, they fail catastrophically. Right? A good example is particle size versus hardness. Right? We have a very nice model that says your hardness goes as inverse the square root of your grain size until the grain size gets too small, at which point the model breaks and it no longer is able to give you an effective prediction of your hardness. Conversely, most of your AI models, like if you're using like a GP regression model or a random forest model, they're very flexible. They'll fit any data set that you give them. But outside of their interpolative range, they can extrapolate very poorly and with massively overestimated confidence. Right? And so a lot of what we've been thinking about recently is how do we take the best parts of each of these individual set of models, the extrapolative capability within bounds of our physical models versus the extreme flexibility of AI models into some sort of scientific AI. I hope that was helpful. And also posed as a question, what's the best path forward for this?
So the next question will be coming from Hugo Gasca Aragon, and it is to any speakers. So is there any basic set of tools from artificial intelligence and machine learning which is fully characterized in terms of metrology that you can recommend? And what is your suggestion to address the huge amount of possible algorithms, which is actually going back to Jason's question, sort of how do you choose the right model and right algorithm for a certain subdomain, a top-down generated strategy or bottom-up case-by-case strategy?
Gosh, that's a difficult question. Yeah, so to my mind, there are sort of, not all artificial intelligence is machine learning. So a lot of artificial intelligence is actually just encoding the rules of logic. So if you've got a database of information and logical connections between that information, you can derive new information. Essentially, a query to a database is giving you new information that would be very difficult to assemble. And that, if the database is operating correctly, the outputs are operating correctly, and you can perfectly be safe to use that type of artificial intelligence.
Mm-hmm.
But the other types of machine learning and things like that are purely based on training data, then you are using the fact that these models are extremely flexible so that they can model any system in some sense. They can, and if you have an appropriate data set to train those models, then the outputs of that system can be used a little bit with confidence within the regime represented by the training data. And so the issue becomes not, can I use a particular machine learning algorithm, but does my particular use case, has it been represented in the training, the training data that the machine learning has learned? And that becomes a different question. So a very good machine learning algorithm can be used in a very poor way if it's got poor training data, or the question that's been asked doesn't relate to the training data. So these are difficult questions, and I don't think anybody's got a particularly great answer for it.
That is a really excellent answer. The only sort of add-on that I would have to that is I would first consider the type of question I'm asking and the data that I have. Let's presume quality, right? And so am I asking questions about how closely correlated are my data points, in which case I might consider starting with an unsupervised technique, something that measures distances between things? Am I trying to pull noise out of my data? In which case I might start with like principal components analysis and knock out the high order principal components. And then starting to ask the question, what type of problem am I trying to solve? Is it a classification problem? In which case there's a box in Weka or scikit-learn of classification algorithms. Or is it a regression problem? Am I trying to get a number from something? Oftentimes classification problems can even be considered regression problems because you can get class probabilities. And so you can get a model that tells you not only it should be class A, but this is how confident I am. Then you sort of start to have to ask the question, once you've identified your problem, how important is interpretability versus explainability? If explainability is sufficient, right, then you can use something like random forest and then do feature ranking after the fact and try to identify what were the important features in your data set for creating the model. If interpretability is important, you might be better off, for instance, with a decision tree or some form of regression tool, GPR, lasso, so forward, right? And so once you sort of narrow yourself down into this box of interpretability, supervised, unsupervised, classification versus regression, you'll typically find that there are a handful of reasonably good models. And from there, the game is hyperparameter tuning on CV splits to see which model gives you the best predictability and interpretable or explainable outcome.
I could just add to that, I think the statisticians are always very keen that whenever you come to that final stage, you've discovered that you've used a model you think is possibly suitable. Make sure you test it and validate it through using cross-validation or something to say, okay, does this model actually work well with my particular problem? And just do that second checking to make sure that you have got some evidence that you've come to a good decision on that.
Yeah, absolutely. And check your validation statistics against your training statistics. You want to sort of find that sweet spot where your training statistics are high, but the gap between your training and validation statistics aren't so large. Last point that I would make is trust CV, but don't overtrust it. There's often information leakage between the folds. And so hold out a data set that the model never sees. Run your predictions on that just to absolutely convince yourself the model works.
The problem here is in the current world, you're being sold a cat in a box by a vendor who produced a system, and you don't even know what data has been trained on. I have encountered cases where somebody tells us this has been trained on 500,000 cases, and you think, wow, 500,000. And if you know the domain a little bit, then you understand that in this domain, 500,000 are generated on 2 machines within half a year. How representative is this model for other systems? Nobody knows, but you're going to pay £100,000 or dollars before you know. It's a bit of an expensive way to find out, I feel, and also very unreliable, given that this case was talking about clinical medicine. So an interesting question to follow up from this is by Denny Hermavanto. And he's asking whether there are many algorithms and methods in the point of view of metrology. Can we make the standard of AI and ML itself? I'm not sure how the standard would look like, but perhaps the speakers have a better idea.
Not really, Alistair.
Well, but perhaps a cookbook on when to use what. I mean, so what Jason has just described as a classic cookbook that they supply with scikit-learn. Now the problem is we're going to things like proper CNNs or GAN systems where you have 2 networks competing with each other, or really deep things like deep random forests or anything else, in fact. So what do you do then? And what is the cookbook there?
Yeah, so I think the metrology community again has to look at what the what tasks it's sensible for the metrology community to undertake, and what is tasks are sensible for the wider scientific community to take. So my own feeling would almost be that if we're trying to come up with reference data with quantified uncertainty, and that uncertainty quantification relies on good scientific principles, then we can only use some of these machine learning models if we can, in a principled way, assign an uncertainty to that model, that uncertainty associated with the modeling component. And unless we can do that, then we should use these systems with a lot of wariness. If we're using those systems for discovery, okay, this is a new phenomenon, or to discover a new phenomenon that we didn't know was there in the data, and that's particularly where machine learning algorithms are particularly strong and particularly effective and particularly useful. That's one thing. But if we're trying to write a calibration certificate where we've put down our uncertainty statement and we've put down our reputation of our National Metrology Institute, then the use of machine learning in that context, it is going to be difficult, I think, at the moment.
Thank you very much. So there is time for one more question. I'm going to ask it at Ian Gilmer. And this is a question by Claudia Swart. And this is: in the light of reuse of data from different sources, how can reliability and comparability be ensured when comparing results from different clinical studies? Or what are the different interpretations between annotations? Annotators. Apologies.
I don't know if Ian can hear. You're muted, Ian.
Oops.
I think Ian is muted again.
Okay. Now you're muted, Marina.
Ouch. I love this. Sentence of 2020. You on mute.
Yeah.
Okay, so the last question would have been from Claudia in how we can ensure reliability and comparability of results from different clinical studies or different interpretations between annotators. But this is a very clinical question. So how basically trustworthiness of your labels?
Well, I think this is another great question. So one of the things that the metrology community does to help with reproducibility is not only do we have a standard set of references and base units and so on, we also work to sort of standardized protocols so that different laboratories are doing things in a similar way. And so one of the issues with taxonomies and ontologies is that there's many such standardized taxonomies and the like, but they're doing slightly different. They're not totally interoperable, and they're doing slightly different things. So an annotation according to one taxonomy might not be interpretable in another taxonomy, and that is an issue. Now, I think in metrology, we've been trying to address very simple systems, measuring the length of a chunk of metal. And so our encoding and annotating that information is reasonably, it's kind of straightforward. So the issue hasn't particularly arisen. But as soon as you start annotating for, issues to do with materials or drugs or chemical compounds, and all of a sudden, and how those chemical compounds and materials were produced, all of a sudden that annotation becomes very important and absolutely crucial to understanding what the data, what system the data is relating to, and there at that point the annotation becomes an issue. And again, I don't know, Jason, if you've got thoughts about how that works in the materials world.
I have so many thoughts. So say it like this. You're going to be generating models from data sets, and you're going to get those data sets from sundry different places, the literature, handbooks, your own instruments, your own graduate students. Look at every piece of data critically. Use techniques like looking for influences in your data set, look for feature importances, deliberately introduce random features or shuffle data when you train your models. Do everything you can to try to identify data sets that are either outliers or have, when you're pulling things out of Landau-Bornstein, there's no error bar. A thing's a glass or it's not. All of the original data that was used to generate that's gone. And so as a scientist, when you're pulling that data and you're building models from it, treat every data point like it's potentially garbage. And only trust it when, frankly, never trust it.
So that's a summary for the conference. Never trust the data.
It's a very positive message.
under any circumstances.
Just to pick up a point on the clinical studies there. So in the pharmaceutical world, where I mostly work in, a huge amount of work goes into so-called robust study design, because I mean that's clinical trials cost tens to hundreds of millions of pounds. So you really want to be as confident as you can in the study design. But it's an interesting point about, in that study design, could more effort be put on in terms of the reuse of the data? Now, the FDA do mandate the requirement for a lot of that, for all the clinical data to be open and accessible, which is very good. But combining data from multiple clinical trials, I mean, there's a lot of good examples of that going on right now with the development of the vaccines. How robust is that in terms of a future robust study design, taking in multiple outputs of previous clinical studies? I think it's a really good question and a big topic, I think.
Thank you. I think it's been a very lovely discussion. So it's been fun, apart from the mute, please. I think we can now go to
very short. And I found the outlook was much more optimistic than in the early morning. In the early morning, we ended with everything is pain, or we enter a lot of pain, and then just saying be careful with data and don't trust ever data is a slightly more optimistic.
There's this fantastic paper, I can't find the reference right now, but there's this fantastic paper from Google where they were using image recognition to look at retinal scans of people's eyes looking for a particular type of disease that's common to people who have diabetes. And I think that they decided to use a set of experts, medical experts, in identifying those things, and the disparity. Like if you have it real bad, all of the experts pretty much agree. If you don't have it at all, most of them agree. If you're in the middle,
yeah.
And so trying to train a classification model from that becomes very challenging.
Yeah.
Okay. Yep. So thank you very much for active participation. I hope you enjoyed the discussion and the session. So tomorrow will be the closing plenary, and it will be from 1 p.m. till 3 p.m. Universal Coordinated Time. And during this, we'll be discussing high-level and technical needs for future development of data, services, and tools for the international system of units with respect to fair digital data. This is it. So enjoy the rest of your day, and I'll see you tomorrow.